Noir plasma chrome bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
All right, let's dive right into this explainer and decode the dense, absolutely fascinating universe of solid-state physics. We're going to build our understanding entirely from the ground up. We'll start with static crystal blocks and scale all the way up to the absolute macroscopic magic of quantum superconductivity. It's really a beautiful progression of rules, where the fundamental geometry of atoms ultimately dictates how energy, heat, and electricity flow through the materials that build our modern world. Here's our roadmap for this journey. We are going to hit crystal geometry and binding, move into phonons and thermodynamics, then electrons and band theory, followed by semiconductors and transport, quantum magnetism and spin, and we'll wrap it all up with superconductivity and synthesis. Section 1. Crystal geometry and binding, the foundation of matter. To start, we really need to understand the structural architecture of a crystalline solid. Now, you might think atoms can just stack together in infinite random ways, right? Well, nature actually imposes strict rules. Rotational symmetries and translational compatibility restrict all crystals into exactly 7 distinct crystal systems and exactly 14 provised lattices. These are the strict geometric rules dictating atomic packing factors, and they basically lay the foundational blueprint for every single property a material is ever going to exhibit. But physicists don't just look at crystals in normal, real space. They use something called reciprocal space. Instead of measuring physical distance, think of reciprocal space as the momentum shadow of a real crystal. This mathematical transformation is the exact blueprint we use to interpret X-ray diffraction patterns via Bragg's law. It literally allows us to measure the invisible, determining exactly how atoms are spaced by looking at how waves of light scatter off their planes. And check out this specific value, 2 times the natural log of 2. This is known as the 1D Madelung constant. It acts as a mathematical blueprint, proving how infinite chains of alternating positive and negative ions geometrically balance out their electrostatic cohesive energy. Think about an infinite line of alternating sodium and chloride ions. They're constantly attracting and repelling each other. This elegant little number proves exactly how that infinite series converges, giving the crystal its structural stability so it doesn't just fly apart or collapse in on itself. Moving on to Section 2, phonons and thermal dynamics, adding heat and movement. Now that we've got our rigid, statically bound crystal built, let's add some heat and see how it actually moves. Imagine trying to track trillions of individual atoms all bumping into each other at once. That's mathematically impossible. So instead, we use the harmonic approximation. We view these vibrations as a massive collective stadium wave of uncoupled quantum harmonic oscillators. We call these quantized units of vibration phonons. They act just like particles, carrying energy and momentum through a crystal. And we can even map them in the lab using inelastic neutron scattering. So the crucial point to understand here is comparing 2 early models of how solids absorb heat. Albert Einstein originally proposed that all the atoms in a lattice vibrate at a single fixed frequency. Brilliant start, but it completely failed at low temperatures. Then the Debye model comes along and triumphs by realizing lattice vibrations are actually complex acoustic waves spanning a whole spectrum of frequencies, up to a cutoff point. This model successfully produced the T-cubed law for low-temperature heat capacity, proving that the entire crystal acts as an elastic continuum, not just isolated atoms humming at a single pitch. Section 3. Electrons and band theory. The flow of charge. Let's shift scales and introduce electrical charge into the mix by examining the free electrons submerged in our vibrating crystal lattice. Now, this number right here reveals something deeply profound about the universe. It's the Lorentz number, a universal constant born from the Wiedemann-Franz law. It proves that the ratio of a metal's thermal conductivity to its electrical conductivity is directly proportional to its temperature. Meaning heat and electricity aren't just loosely related, they are beautifully and mathematically linked through the exact same mechanism of electron collisions inside the crystal. But electrons don't just fly around freely. Without getting lost in the weeds of the Schrödinger equation, we can look to Bloch's theorem as our master blueprint. It proves that when electrons interact with that periodic repeating potential of the crystal lattice, their plane waves are modulated. As a direct mathematical consequence of this, forbidden energy band gaps literally rip open at specific momentum boundaries. Electrons are strictly forbidden from possessing energies within these gaps. No exceptions. And this builds our entire material classification system. Picture the Fermi sea of electrons as a huge quantum traffic jam. If there are empty lanes just ahead of the traffic, the cars can easily accelerate. That's a metal. If there's a massive concrete barrier ahead, everything stops entirely. That's an insulator, marked by a massive band gap. But if that barrier is short enough that just a little bit of thermal energy can help cars hop over it, you get semiconductors. Which brings us perfectly to Section 4, Semiconductors and Transport, Engineering the Gap. Since semiconductors are quite literally the engine of our modern tech world, we need to understand how they balance electrons and the empty spaces they leave behind when they jump that gap. Spaces we call holes. This elegant little equation is the law of mass action. It states that in thermal equilibrium, the number of electrons multiplied by the number of holes is always a constant value for a given temperature. This means whether we artificially dope a silicon chip to have a ton of extra negative electrons or extra positive holes, nature firmly insists that their multiplied product remains perfectly constant. If one goes up, the other simply has to go down to maintain balance. So how on earth do we measure how heavy these electrons act inside the crystal? We use cyclotron resonance. By spinning these charge carriers in a static magnetic field and hitting them with microwaves, experimentalists find a resonant frequency. This allows them to directly measure the effective mass of the electrons. And here's the wild part. Because the crystal lattice is constantly pulling and pushing on them, an electron's mass actually appears to change depending on which direction it travels through the solid. Section 5. Quantum magnetism and spin. Collective alignment. We've added heat. We've mapped the charge. But what happens when we introduce a magnetic field to the intrinsic quantum spin of these subatomic particles? To figure out how naturally magnetic an individual atom is before it even joins a lattice, we just follow Hund's rules for unfilled electron shells. It's a simple 3-step quantum rulebook. The electrons first maximize their total spin to stay as far away from each other as possible, which minimizes Coulomb repulsion. Then they maximize their orbital angular momentum. Finally, they calculate their total angular momentum based on whether their subshell is more or less than half full. Basically, nature is ruthlessly efficient at finding the lowest possible energy state. But atoms aren't isolated, right? When they interact in a lattice, the quantum mechanical Heisenberg exchange dictates if they align parallel to create a ferromagnet, just like the magnets on your fridge. But magnetism isn't just a static, frozen property. Remember those phonons we talked about earlier? Well, heat also creates ripples in the magnetic field called magnons. These are quantized spin waves that cascade through the ordered magnetic domains. As the temperature rises, these magnons create chaos, steadily weakening the overall magnetic force until the material hits a critical temperature and loses its bulk magnetism entirely. Finally, Section 6, Superconductivity and Synthesis, the macroscopic quantum state. For our final progression, we reach the absolute most complex state of matter, where classical physics takes a back seat and electrical resistance drops to absolutely zero. Phenomenologically, we've got two main types of superconductors. Type 1 completely blocks magnetic fields from entering its interior, acting like an impenetrable shield, which is known as the Meissner effect. Type 2, though, is far more exotic. When the magnetic field gets strong enough, it actually allows tiny, quantized tornadoes of magnetic flux, called Abracosa vortices, to pierce right through the material, while the rest of it remains perfectly superconducting. This localized vortex state is exactly how our most powerful modern electromagnets, like the ones in MRI machines, can operate without failing under extreme magnetic pressure. This is where it all clicks. Ginzburg-Landau theory proves that the magnetic flux inside those Type 2 tornadoes is strictly quantized. But the real breakthrough is BCS theory. It proves that electrons, which usually aggressively repel each other, can actually bind together into Cooper pairs. And how do they do it? Through the exchange of phonons. That vibrating crystal lattice we started with is actually the very mechanism that binds these electrons together, allowing them to surf through the material as a single quantum entity with zero resistance. We know this for a fact because changing the mass of the crystal's atoms directly changes the critical temperature, an amazing phenomenon called the isotope effect. All right, let's tie this whole thing together with a capstone synthesis. We started at the scale of 1 to 5 angstroms, looking at how crystal structures form a rigid grid. We saw how the harmonic approximation gives birth to phonon waves. We watched Bloch's theorem govern electrons, Heisenberg exchange govern magnetic magnons, and finally, BCS theory unite electrons and phonons to create superconducting Cooper pairs. This perfectly maps how the strict geometric blueprints of atomic arrays dictate the creation of exotic quasi-particles at every single scale of matter. Solid-state physics essentially hands us the ultimate cheat codes to the universe. We figured out how the underlying geometry controls the heat, the electricity, and the quantum magnetism. But now that we are engineering entirely new, synthetic, low-dimensional materials from scratch, pushing way beyond naturally occurring crystals, what previously impossible quantum realities are we going to unlock next? Think about that next time you look around at the screens, batteries, and processors powering your world today. Thanks for joining me on this explainer, and keep exploring.
Like what you shared.
This website makes learning so easy. I found all my resources here.
Noir plasma chrome bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.